Let us solve some problems involving adjunctions. So here's problem 1. Let AB denote the category of abelian groups. So the objects are abelian groups and arrows are just group homomorphisms. And let group denote the category of all groups. And let's define G from AB to group to just be the usual inclusion functor. That is, given an abelian group B, you take it to B itself, which you think of now as a group. Forget the fact that it was abelian. And given a group homomorphism, so GB is equal to B and GF, given a group homomorphism F, you take it to the group homomorphism F. And you define F from group to AB as the abelianization functor. So F of a group A is A modulo its commutator subgroup. So let me remind you what this is. Is the smallest normal subgroup of A. Containing the set of all commutators, i.e. the set x, y, x inverse, y inverse, where x and y are in A. This thing is usually called the abelianization of A. Okay, so here's your exercise. Show that F comma G form an adjoint pair. So it would be a good idea to pause your video at this point and go back and look at the definitions from the lectures and try to set up exactly what you need to prove in order to establish this, and then do it. If you can't do it, then you can watch me solve it. So here's the solution. So what we need is to set up the following thing. So for every A group, that means object of group, we need to define eta A to G circle F of A such that for every object B of abelian group, and every group homomorphism A to we want to say B here, but we're saying GB, which is that we're just thinking of B now. It's an abelian group, but we're just thinking of it as an object in the category of all groups. So for every group homomorphism here, we have there exists unique F sharp from FA to B such that this diagram commutes. So this is G of F sharp. Okay, and this eta needs to be natural. That means this collection needs to give rise to a natural transformation. So let's just decode what all these symbols mean. So what we have is so this diagram A is just, now it's a group, and F of A is, well, it's the abelianization of the group. So A mod AA, and we need eta like this. Now this is technically, this is well, this is going to be an arrow in the category of groups, right? So this is an abelian group, you can check, but when we just think of it as an arbitrary group, so we need an arrow like this, and what else but just take the quotient map. You need to check that it's natural, but that's not difficult, and I'm going to leave it out. And what you're saying is that for every abelian group B, whenever you have a group homomorphism from A to B, that means every group homomorphism from A to an abelian group factors through the abelianization of A. So what you're saying here is there is a group homomorphism F hat from A mod AA to A. And this is actually very easy to see. You just define, well, it's forced F hat of A, the coset AA, to be F of A. And you need to check that this is well defined and that it is indeed a group homomorphism from A mod AA to B. But these are all standard, and I'll leave it to you to work out all the details. Okay, let's look at problem 2. Let C be any category where coproducts exist. Which means that given any two objects A and B, you have a coproduct which we denote by A plus B, right? Now we have a functor coprod. We can think of coproduct itself as a functor. It goes from C cross C, the product of the category C with itself. So its objects are pairs of objects in C to C. And what does this functor do? It takes A comma B to A plus B, and you can work out what it does on arrows as well. If you have a pair of arrows in C, it will define arrows on the coproducts. And then we have a functor called diag from C to C cross C. And this is the functor which takes any object A to the coproduct. No, not the coproduct, to the pair A comma A. And the problem is, show that coprod comma diag form an adjoint pair. So you should again go back to the definitions and try to see exactly what you need to prove and try to do it yourself. But if not, you can watch me solve this. So again, we need to set up this eta from the identity functor of C cross C to to the functor diag circle coprod. So this is what we need. So let's see what this diag circle coprod is. So diag circle coprod of, so this is a functor from C cross C to C cross C. So we will give it an input of two objects from C. Now coprod takes this to A plus B, and then diag takes it to A plus B, comma A plus B. Okay, so what we need is eta A comma B from an arrow in C cross C from A comma B to A plus B, comma A plus B. And how will we do that? Well, you just define it by, so remember, when you have a coproduct, let me just recall for you the universal property of the coproduct. So when you have a coproduct of A and B, A plus B, then you have an arrow from A to this coproduct, which we call usually IA. You have an arrow from B to this coproduct, which we call IB, and it has the universal property that whenever you have arrows from A to some object, let's say C, let's call it FA, and you have another arrow from B to the object C, then you have a unique arrow which we'll call F from A plus B to C. So in particular, this coproduct comes with arrows I subscript A and I subscript B from A and B. So we can take eta AB to be the most natural thing, namely I subscript A, comma I subscript B. I subscript A is from A to A plus B. I subscript B is from B to A plus B. And what we have now is A comma B. We have eta AB. So this is I subscript A, I subscript B. And we have A plus B, comma A plus B. So this is diag circle coproduct of A comma B, and we want to show that whenever we have an arrow from here to diagonal of C, so diagonal of C is going to be C comma C for any object C of the category C. So whenever we have this, well, every arrow here from A comma B to C comma C is going to be of the form FA comma FB, because it's just the arrows in the category C cross C are pairs of arrows in the category C. So an arrow from A comma B to C comma C is going to be a pair. One arrow F subscript A from A to C, and another arrow F subscript B from B to C. And when you have this, it's easy to figure out what to put here. You just put F sharp to be F. You just take F. Now if you take F and you take diag of F, so diag of F is just F comma F, where F is as defined by this universal property of A plus B using the arrows FA and FB. Then from this universal property, it follows that this whole diagram commutes. Now I leave it to you to work out all the details, but this proves that the diagonal and coproduct functors are adjoints.